Yeah, what I'm going to talk to you about today is molecular knots. And of course, you'll all be familiar with very much the reason why knotting is now interesting. Knots and links are, of course, basic elements of structure in all kinds of tools, materials, symbolism. And we all know that humans are not the only animals to be able to tie knots. Great apes can tie rudimentary knots. Knots have been tied on this planet for perhaps a million years. These spherical stones that are found date back to the lower Paleolithic times, and they're believed to be bowlers, these weapons that hunters can use to, where the stones are attached to ropes, and they throw them around their heads and use them as to bring down animals and as weapons. And if these spherical stones are really bowler, then in order to be attached to the ropes, the humans would have had to have tied knots. So that meant that humans were tying knots maybe a million years ago, which is about the time that humans started to use fire for the first time. So the tying of knots is a really ancient human civilization. And the oldest surviving knots, or woven materials in this case, are actually about 10,000 years old. This is an amazingly well-preserved basket that was found in a cave in Israel, preserved by the very dry climate there. But of course, as you are very familiar, knotting and weaving is about more than just pure topology. It's about the restrictions that these entanglements make in allowing the movement of the components. And for that reason, biology also uses knots. Knots are found in DNA, in something like 1 or 2% of proteins, and of course any polymer of any length and flexibility will fall entanglement. So there's great contemporary interest in all kinds of knotting in many fields, not just molecules, but I know your center is extremely broad in what it does in the field of knots. And the crucial thing, of course, that we know in the big world that what knot you choose to use for a function is very important. If you're hanging off the side of a mountain, you want to have something like a stopper knot. Is this working? Maybe I've switched it off, have I? Here we are. I think it's I switched it on now. Okay. If you're hanging off on a mountain on a rope, you want to have something like a stopper knot securing you, not one of these slip knots. Otherwise, bad things can happen. And actually, knotting dates back in terms of the fields of topology, date back to chemists and Lord Kelvin wondering whether knots in the ether actually corresponded to different atoms. And he had his colleague, Peter Guthrie Tate, tabulate knots. And this is one of the earliest knotting tables that he produced, where he began to tabulate for the first time all the different sorts of entanglements that you can have with knots. And theoreticians have actually tabulated more than 6 billion different prime knots with up to 23 crossings. But until recently, chemists had only been able to make one topologically non-trivial knot. That's the trefoil knot up here. And this is really the reason why we became interested in this field, because obviously, if it's possible to make lots of different knots, chemists should be able to do those, to find out what sort of knot would be interesting for a particular purpose. And only being able to form a trefoil knot denies access to this whole field of different molecular topologies that would be difficult to make. So my group, actually our main interest, or a big interest of our group, is in making molecular machines. And to do that, we use architectures that are typically threaded, such as these type of rotaxanes, or their links. So like this 3-catenane motor. And the techniques that you need to use to form threaded molecules and linked molecules, to do that, you need to control how molecular strands cross over each other. And of course, that's exactly the same sort of strategies that you need to form molecular knots. So what I'm going to talk to you about today is the work that we've done over the last 10 years in taking the concepts that we developed in this sort of area and applying them to the making of molecular knots. And when we started this work, several trefoil knots had been made, many just isolated by chance from reaction products when people were trying to make macrocycles or oligomers, and they actually resulted in knots. And there were a few examples of design syntheses of knots. This very famous one, the first synthesis of a molecular knot by Jean-Pierre Sauvage, and then a few others over recent years. And what these all have in common, and the systems that I show you today have in common, is that they're all formed by self-assembly. And I wanted to try and demonstrate to you all the concept of self-assembly today. Actually, I got up in my hotel today and I went to get the newspaper, but actually some child had got to it before me, which made a real mess of it. But it did get me thinking that, of course, a newspaper is a very complicated structure that requires lots of effort for people to put together every day. You need the journalists, for example, to write the articles. Then you need the editors to actually copy edit what's been made. You need illustrators, either perhaps cartoon writers or photographers, to illustrate the articles to make it attractive. Then you need, of course, to have it printed at wherever the print shop has to be. And then finally, it has to be circulated to the convenience store or the railway station or the drugstore, or in my case, the hotel, to actually finally get the newspaper in its fully constructed form that we can all read. And it's a really complicated job that takes lots of effort from lots of different men and women every day to put together. And I wonder, wouldn't it be easier if there was a way to just take these building blocks and then get them to self-assemble to actually form, no, but you're too kind, self-assemble to form the kinds of structures that we want. So this is the type of thing we try and do in our research group. We try and get the molecules to do the work and use those to actually assemble the building blocks. So so it's a relatively new field of synthetic chemistry, being able to make topologically complex structures. And even as recently as 2010, so just a decade ago, then the isolation of a trefoil knot was publishable in Science. And this is an example from Jeremy Sanders, a chance discovery of an organic trefoil knot. And in that paper, he explains why this is such a difficult challenge. The synthesis of molecular knots is particularly difficult, said Sanders, because it requires precisely defined pathways and transition states that are entropically much more demanding than simpler macrocyclization or just linking processes. So it's still difficult, but as I've showed you, as I'll show you today, a lot of progress has been made in the last 10 years. And the approach that we take our group is really a traditional one in lots of areas of science. We design our strategy to the synthesis, and then we start to investigate whether this design will work. And almost always, or always, there's problem solving along the way. If it just worked as we predicted, you didn't actually discover anything. And almost always, all our time is spent solving problems because the designs that we make don't quite work. And to solve these problems requires good observation by the students and the postdocs, sometimes some luck, as again, we'll see some examples of that later. And then once you've solved this problem, then you've discovered something new, and your understanding of how to tie more complicated knots has improved, which then allows you to design syntheses of more complicated structures. So as we go through, I hope you'll see that the structures that we synthesize are much more elaborate than the early examples. So this field started with my friend Jean-Pierre Sauvage, who had come up with this great way of doing metal templated synthesis of catenanes, simple links by linking phenanthrene units to copper-1 ions. And if you close the N groups, A with B and X with Y, this will form a 2-catenane. And Sauvage realized that if you could form a linear helicate, and it extended that to have 2 copper atoms, and you connected A and B and X and Y, then you would get a trefoil knot. If you extend these linear helicates further and close the N groups again, A with B and X and Y, you can get a doubly interlocked catenane or a Solomon link. However, that's the limit of this linear helicate strategy. And in principle, if you had 4 or 5, you could get more complicated architectures, but these don't work because the longer the linear helicate is, then A will not close with B, it will close with sometimes with B, sometimes with Y, sometimes with X, sometimes in an intermolecular way. And you, this strategy just doesn't work for long helicates. So we wondered whether it was possible to solve this problem of these groups being too far apart by using circular structures, circular helicate structures like this. That way, you would only need to have small ring closures, connections to form ring closures, and it might be easier. The disadvantage over this approach is you only need to close 2 connections here, and here you have to do 5. But this having a short distance, a well-defined short distance and geometrical arrangement might allow us to do that. And circular helicates have been discovered by chance by Jean-Marie Leigh back in the 1990s. And he found that these tri-BP type ligands, when treated with iron salts, form circular helicates. And if you had chloride present, they formed this pentameric type of helicate. And if you didn't have chloride ions and had other kinds of anions, they formed hexameric helicates. And it looks like if you just connect the N groups here, you would form a pentafoil knot, and here a more complicated link. However, it's a little bit more difficult to do that than it sounds, because if you note here, the conditions are very harsh. You have to heat this at 160 degrees in ethylene glycol because the coordination of ion chemistry is so slow. And then also, although this looks nice in the ChemDraw structure on the slide, actually these N groups point directly away from each other. And so being able to connect them round together would be very entropically difficult. You would cost a lot of degrees of freedom of the chain to fold round to do that. Then, as we've mentioned, you need to have multiple connecting reactions. And that means that these have to go either in very, very high yield or if a mistake is made, for example, this group connects with another molecule, for example, you have to have reversible reactions so that you can correct those errors during the reaction. And the reaction will proceed under thermodynamic control to give you the most favorable structure that you designed to be your knot. And so we modified Leigh's design to get rid of the BPI units from these two end groups and replace them with these single pyridine groups with an aldehyde. And that aldehyde can condense with an amine to form an imine to form the bidentate group that's needed on the terminals. And that is a dynamic reaction, which means we can use much lower temperatures than Leigh used. This occurs at 60 degrees in DMSO, and this is reversible, so it will do the error correcting. And sure enough, if we take this ligand and this particular bisamine, we can form this pentafoil knot in reasonably good yield, 44% yield. However, this reaction is very selective for this bisamine with these two oxygen atoms in the chain. If we take chains of exactly the same length or longer or shorter, but these oxygen atoms are replaced with CH2 groups, then you don't get any knot formed. And that's just, again, part of this discovery process. Initially, we were using these sort of chains and not forming anything. And then the student tried this bisamine and it worked. And the reason for that we'll find out a little bit later. How do we know that we have the knot? Well, this is the X-ray crystal structure of that knot. And to show you that this ligand strand really is knotted, if we start here in the middle of this blue unit, then if we follow it round clockwise, we go over, the strand goes over here, then round the metal ion, then under, then over, round here, and then under, over, round, under, over, all the way round, under, over, round again, under, and back to the start. So this is one continuous loop. It's got 160 atoms in that continuous loop, and it's made in one step from this self-assembly reaction of 5 of those dialdehydes, 5 of those diamines, 5 of these iron cations, and 1 chloride ion held in the middle that templates its assembly. And if we rotate the crystal structure, you can see this lovely double helix that's formed from the ligand around the metal ions. And even though this is a simple assembly process, it sort of belies the complexity that's involved in the design that leads to the assembly of the knot. So first of all, you need to have this metal template helicate formation. It needs to be a helicate because that creates the crossing points that all have the same handedness, and you need to control the handedness in these crossing points so that it goes over under each time. So the metal template helicate formation is crucial. Then the spacer between these binding sites is also crucial because you need to have a cyclic helicate rather than a linear helicate. And for that, you need just these 2 carbon atoms. If you have more than that, it'll form a linear helicate. The anion that's at the center here controls the number of crossings. So if you have chloride here, we get 5 crossings, and the reversible imine bond formation allows error correction so that even though we've got 5 crossings, if any one of them forms in the reaction that is a mistake, it'll be, because these reactions are reversible, it'll all go through to the thermodynamic product, which is actually the knot. And finally, by looking at the X-ray structure, we can see why these 2 oxygen atoms in the spacer are so critical to the synthesis. And it's because if these oxygen atoms were CH2 groups, you'd have 1,3 steric interactions between the CH2 groups here and other hydrogen CH2 groups around the structure. So having these oxygen atoms removes that, and also having an O-CH2O interaction leads to something called the gauche effect, a stereoelectronic effect that actually favors this gauche conformation around here, which favors, again, this curvature in this chain, which favors link closing. So there's a lot of different design elements that feed into this assembly process. But having developed that, we can apply those techniques to other kinds of knots. So this, a few years later now, we've replaced the imine chemistry with ring olefin metathesis to close the end groups here. And this strand contains an oxygen atom between these two CH2 groups, which favors the formation of a tetra circular helicate. And this long spacer here means that these two groups stick out so that only these double bonds can connect together, not this one and this one, say. So this gives us the connectivity that actually forms this kind of structure. And that molecule is an 8-crossing knot, a so-called 819 knot. And this is an example of a non-alternating knot. So instead of going over, under, now we're going to have a different non-alternating crossing pattern, which will go over, under. So if we start here and we go around clockwise again, you'll see that this ligand strand goes under, then round, then over, under, round, over, under, over, under, and round, over, and back to the start. So this is a 192 atom continuous loop. It's got 8 non-alternating crossings now, and this one's made in 2 steps. You assemble the helicate, and then you do the ring closing metathesis to capture the structure. And actually, this is the tightest physically knotted structure that's known, and it appears in the Guinness Book of Records as the tightest knotted structure for a bit of fun. If we rotate the crystal structure, you can see this is a much flatter structure than we've seen before. And now these are triple helicates, these strands. If you look around this metal ion, you'll see that there are 3 of these BPI units. So this is a triple helicated unit to form this knotted structure. Okay, so what are the consequences? We can make these kinds of knots. What's the consequences of having this knotted structure? Well, one of the key features of this template method of making the knots is that these chloride ions and other anions are held very tightly in this cavity, which is the reason that they template the knot. They're held very tightly by the CH hydrogen bonding interactions of these BPI rings. These are very electron deficient because the metal ion is drawing the electron density away from them. So this forms very strong CH to chloride hydrogen bonding. And it turns out, well, we can see that in the NMR spectra. So if you pull out the chloride ion by adding silver salts, then these protons that are hydrogen bonding to the chloride ion, they shift nearly 1 ppm in the NMR spectra between the empty cavity and the chloride cavity knot. And in fact, these knots are some of the strongest binders of chloride that are known. They have a binding constant of about 10 to the 10 in acetonitrile. And so this binding is so strong that these empty knots will actually sequester chloride ion from solvent, from glassware, unless you keep them in the presence of silver salts or other halophilic sort of sources. So this knot is actually one of the strongest non-covalent binders of chloride ion that's known, and we can use that in its chemistry. So if we have formed our knot, we can actually remove the metal ions by treating it with sodium EDTA, and then the knot is completely stable, but it doesn't have any well-defined form. So when you've pulled the metal ions out, this knot won't bind to chloride or anything else because it's missing the metal ions. But we can reintroduce metals, and the easiest one to introduce is zinc, because it has the same sort of coordination geometry as iron, but it has much faster kinetics. So that reassembles, by adding the zinc, it reassembles this anion binding site. And if we've used BF4 ions, they don't go inside. So this has got this empty cavity that's a very strong binder of halides. So if we treat that with with an alkyl halide, such as this trityl bromide, this will actually strip the bromide off, the knot here will strip the bromide off this molecule to form the trityl cation, and that trityl cation can be used to do chemistry. So for example, it can be used as a catalyst to promote Diels-Alder reactions and Michael addition reactions. So this knot can actually produce the catalyst for this chemical reaction. Once the bromide is in the center here, we can then remove the metal ions again with sodium EDTA and reform the knot. So this is an example of allosteric binding. So the binding of the metal ions by the knot creates another binding cavity for something else. And it's sort of an example of what knotting can actually do. If you don't have a knot here, if you just have linear helicates, they won't form any kind of cavity. So what having this knotted ligand does is it restricts the conformation and the dynamics of how these strands would normally want to adopt if they weren't in this knotted topology. So the knotted strands allows these higher energy structures to be generated because it can't adopt the lowest energy structure that you would have if you didn't have a knot here, if this was just a linear polymer or linear oligomer. And this is a sort of a general property, I think, of or illustrates this general property of knotting or entanglements, that it restricts conformational freedom of units. So we can use not just transition metals to form, to template the assembly of knots, but we've also used lanthanides to do that. If you take any lanthanide in their 3 coordination, in their 3+ state, they'll assemble 3 of these ligands around them, coordinating to the 2 oxygens here and the nitrogen. So it's a 9-coordinate lutetium example here. That, having these aromatic groups here organizes these strands so it holds these double bonds, these olefins close together, so you can do ring closing metathesis to close the end groups here. And this will form trefoil knots. There's no chirality in these structures, so you'll form both enantiomers of the trefoil knot, so 2 mirror images. However, if you introduce a chiral center on these ligands, you can actually get just a single topological enantiomer of the knot. So just the knot being either having either lambda helices or delta helices. So a single topological enantiomer of the knots. And this is an X-ray crystal structure. Sorry, it's a bit dark to see, of just a single enantiomer of one of these knots. So this is nice because the coordination chemistry of lanthanides is generally rather orthogonal to transition metal template chemistry or coordination chemistry. So that means that we can mix the coordination binding groups in a single ligand strand, as we've done here, to produce new kinds of effects. So this contains the 3 lanthanide units, lanthanide binding units, the 3 units that we need to bind to a lanthanion, and also the 2 units, the lanthanide units, which will bind to a copper ion. And we can use this to tie this ligand strand in a number of different ways. So if we don't add any metals and just link them together by olefin metathesis, we'll just form a big macrocycle, a so-called unknot. If we just add lutetium to it or another lanthanide, that won't bind to the copper ion. So just as we saw before, it'll form a trefoil knot. However, if we add copper to this compound. It'll form a loop between the copper binding sites here, and then the lanthanide binding groups have to thread through that loop, and that leads to a different kind of knot. And it's sort of illustrated with this movie. So this is the strand. It can bind, the phenanthrene units will bind to the copper, and they can bind either way round, either the copper that way round, or these ligand strands can switch so that they're this way round. But when they're this way round, here we've got the chiral groups around the lanthanide group. So this can only thread one way, and they thread through the copper loop. We can close the end groups there, then we can remove the metal ions, and we've got a new kind of knot. It's a 5-crossing knot, but it's different to the pentafold knot we saw before. This is a 5-2 knot, rather than the 5-1 knot. So it has a different unsymmetrical kind of geometry that we couldn't make any other way. So this is an unsymmetrical knot. You can't make this from the sort of symmetrical template systems we've been working before. And we call this a metal ion chaperone effect, because just as proteins are folded by chaperones to adopt particular shapes and conformations, here we're using these metal ions to control how this strand folds and entangles in order to form the particular knot that we want to assemble. And I think this will be a very powerful strategy going forward for understanding how to tie different kinds of knots. And while we were doing this, again, we discovered something that we didn't expect. The student who was doing it made this, the trefoil knot with just lutetium templation. They took the NMR spectra of the crude material, could see that it was this lovely lutetium coordinated knot, and then they columned it on our gel permeation chromatography unit, and the person who'd been using it before them had been chromatographing, purifying a compound that had got some copper in it, and there were some copper residues on the column. And when the knot came off the column, the NMR spectrum looked completely different. And when we did mass spectrometry, we saw there was no longer any lutetium in the knot, there was copper. And the copper had displaced the lutetium. Where in this, in the trefoil knot, it can't bind both ions at the same time because of the conformational restrictions on the structures. So what had actually happened here was that the copper had displaced the lutetium to bind with the copper binding ions, and that leads to a different conformation of the knot. This has got a rise of -4 instead of a rise of 3, even though it's the same knot. It's got a different conformation. So this is like molecular cat's cradle, this game that children play where they twist loops into different structures. Here, the copper replaces the lutetium and ties it into this new conformation of the knot with a different rise and different strain in the actual knot just by changing the metal ion. Being able to make knots also allows us to answer fundamental problems about the role of knotting in a polymer chain. And this is new work that's not published yet. It's submitted for publication. So 25 years ago, there were famous papers published, theoretical papers on that knotting may weaken molecular strands when they're stressed, and there were experiments done with optical tweezers tying actin filaments in a strand that showed that. But these are not single molecular strands. These are actually hundreds of atoms thick, and they're sort of half a micron thick. So these are not single molecular strands. But being able to make now individual molecular, synthetic molecular knots allows us to actually study these processes for the first time in well-defined systems. So polymer chains can be put under stress using sonication in what's called mechanochemistry. So if you sonicate polymers, it will elongate them in collapsing bubbles that puts a lot of stress on them, and they'll fracture at particular points. So you can add to these polymers groups that will undergo chemical reactions under stress, and those are called mechanophores, that will break easier than other kind of functional groups, and then get well-defined breaking points. So what we did is that we made one of our knots, one of these lanthanide templated systems, and then we closed the ends of it with a mechanophore, something that will be broken by a strain. So then we put this polymer into sonication, and when it's pulled, the first thing that breaks is the gate here. And once that's broken, then we've got a trefoil knot, but an open trefoil knot in the polymer chain that's being stressed by the sonication. So then the knot will be contracted by the pulling that goes on, and scission will occur. And we can see how easy that knot is to break, and also where it breaks. And these are the results. So if we look at compound 3, so this is just where we've got the ligand that isn't knotted in the polymer, and this is this is just a sort of showing how easily broken the polymer is. So this is a polymer that isn't easily broken because it's has a very shallow gradient here. If we look at this polymer 2, this is the one that has the very easily broken group, the mechanophore in it, but it doesn't have a knot. And that is a much more easily broken polymer than this one. And then this is the knotted polymer, which has got the mechanophore in. And we can see that this breaks at exactly the same rate as the mechanophore. So this tells you that as soon as the mechanophore breaks, then the knot tightens and it breaks with the same weak energy as this mechanophore. So when this isn't knotted, it doesn't break. When it is knotted, it breaks at the same strength as that mechanophore. So this is an experimental demonstration that demonstrates on a single polymer chain that knotting substantially weakens a polymer chain. So more than that, we can actually, so this is actually what's happening here, and we can actually see the fragments of where the knot breaks. And by looking at the products that we isolate, we can see that the knot breaks at these points here, which are actually the entry points to the knot, just as theory predicted 25 years ago. So this is what this is theoretical modeling of this actual structure, and we can see exactly where what actually happening. Stretching of this knotted polymer chains distorts the bond lengths and angles, and it breaks at the entry to the knot. So as knotting occurs, of course, in any polymer of sufficient length and flexibility, this is the first experimental evidence that knotting likely just intrinsically weakens the tensile strength of polymeric materials. So we're very excited about the possibilities that being able to make knots will give us for analyzing the behavior of knots in different processes. So this is another type of not based on helicates, not based on this metal ion chaperone folding. This knot has got 7 crossing points. It's the so-called endless knot. It's the simplest Celtic knot, and its structure appears in lots of different symbolism and manuscripts. This is the Book of Kells in Dublin, a very old medieval manuscript, and it's also the simplest Chinese knot. And this orientation, where we've got these two nugatory crossings, it looks like it has 9 crossings, but it doesn't. It has 7 like this one, because these two crossings are nugatory. That is, they're false crossings. If you just twist here, you can undo them. This gives you a clue about how this can be made from a 3x3 interwoven grids by closing the end groups in this kind of way. That all sounds good, except that 3x3 grids, when we started this work, were unknown in chemistry. And the reason for that is that entangling rigid strands puts strain on the molecules and stops them happening. So we first set up trying to do this, these studies with a 2x2 grid and closing the end groups there to form a Solomon link, a doubly interlocked catenane. This is the X-ray crystal structure of a molecule that we made with a particular ligand strand that forms these nice over-under entanglements. So we figured that what we needed to do was to just extend this ligand strand in to add extra units to go from a 2x2 binding site to a 3x3 system. So we just extended it and added an extra group here. But this is where this process of problem solving came in. When we made that longer ligand, we still couldn't form 3x3 grids. So we started to vary the coordination properties of these different groups, increasing the electron density of this difficult middle group to try and force it to form complexes. And but still, even with this one, when we added zinc triflate to this molecule, it didn't form anything that looked like a 3x3 grid, and nothing happened. But this is where the observational skills and the problem-solving skills of postdocs and PhD students become important. The postdoc working on this project remembered the X-ray crystal structure of the Solomon link that we'd done. That was of a BF4 salt. And he noticed that in the crystal structure, these BF4 anions were actually in the center of these cavities. So he switched from using zinc triflate to zinc BF4. And when we did that with exactly the same ligand, immediately we formed a very quantitatively, a very simple NMR spectrum. And this turns out to be the 3x3 interwoven grid. How do we know that? Well, this is the X-ray crystal structure of that grid with the end groups modeled on here to form the pentophil knot. And you can see that the reason that it forms are indeed these BF4 groups that are found in all 4 of these cavities and stabilize the formation of that 3x3 interwoven group. So we didn't design that at the start. That was a problem that we had to solve, but now we understand that design element. We can use it in the construction of other molecules. And if we rotate around here, we can see that it's a completely flat structure with the metal ions in the center of these 3x3 grids, and it has the same topology as a Chinese knot with the nugatory crossings at the end. So knotting, of course, is related to weaving. They're both achieved by controlling the crossing of strands at particular points, and you need to control their stereo control those crossings, whether they're over or under, and control the connectivity in order to form a continuous woven structure rather than a mess. And we noticed from this crystal structure that we had of that 3x3 grid that it actually forms layers. And within those layers, the 3x3 grids are actually flat, and the end groups all point towards this cavity, central gap in the structure. And if these end groups were connected, then the strands would just go over, under, and form a woven structure. Of course, errors can be made. So this strand doesn't have to connect across here. It could connect to one that's switching from going across to being orthogonal, but it would still be woven. It would just be that the woven strand would change its orientation in that approach. So we took that ligand strand, we changed the end groups to have thiols on the end, because those are thiols can be connected together to form disulfide linkages by just the presence of oxygen, which can feed into a solid material. And we took the preformed grids and put them in solution, and they formed under an air atmosphere, which is going to oxidize. They formed films on the surface. We then treated it with cyanide to remove all the metal ions, so that we obtained a purely organic, no metal ions present at all now, so a purely organic polymeric material which had this flat, flaky structure. And this is a movie of what's actually happening here. So we take the ligand strand, we've got the metals with the BF4 groups present, and those will form grids. With the BF4 groups templating the formation of the 3x3 grid. And then these thiol groups on the end, the grids crystallize, and the disulfide groups are oxidized to connect together to form disulfide linkages. And that forms this extended layers on the surface. And these layered structures are just like the X-ray that we saw before. They've got these layers of anions in between the structures, which stop the polymerization going in 3 dimensions. They're just in 2-dimensional layers. We then remove the metal ions and the anions by treating them with cyanide. And then this wholly organic woven polymer that has this layered structure. And if you use AFM on these layered structures, they're atomically flat for microns. So that this is not a 3-dimensionally polymerized material. It's just polymerized in 2 dimensions. And you see these 4 nanometer steps as the AFM moves along, because as it gets to an end of the layers, it just drops down to the next layered structure. And as you go across, it forms these 2 nanometer stretches. You sometimes see these wrinkles, which is the same sort of thing that you see with graphene sheets, where they've sort of ridden up. And sometimes you just get an individual sheet on its own. This is just one molecular layer thick. And you can see there are some defects in it, but they're all, again, this 3 or 4 nanometer of height. So this is a single layer of sheet of this woven polymeric fabric. And this also appears in the Guinness Book of Records as the finest woven fabric that's known. So the Ivan sheets, silk sheets that he sleeps on, those have got a thread count of about 100. Whereas this has got a thread count of about 40-60 million strands per inch. So this material just tears like a fabric. If you pull on it, it will tear in 90-degree strands. It delaminates, again, just like a normal carpet, just by when you put force on it. So if you put this material on a polymeric sheet, on a plastic sheet, and pull the sheet, it distorts with these 90-degree, at these cracks at these 90-degree angles. And if you have layers of the sheets and you pull them apart, they just delaminate, again, like we see here. Forming this woven sheet changes the stiffness of the material, so we can compare the properties of the 2D woven polymer with a 1-dimensional. We just take the ligand strand and polymerize it, so it forms a spaghetti-like 1D polymer, which has got exactly the same chemical constitution. It's just that it's not woven like the 2D polymer, and they have different properties. So for if you press on it with an AFM, if you press on the spaghetti-like 1D polymer, it's relatively easy to deform. It's got a low Young's modulus. And if you press on the 2D woven material of exactly the same strands, but they're woven, it's much, much stiffer of a material. We can also use this as a sort of a molecular net or a molecular grid, again, comparing to the 1D polymer. These are colored anions because they've got the metal ions here, so they're actually colored. This is a small colored ion, and the gaps in the mesh of this 2D polymer are about 2 nanometers. So this kind of dye will just pass through them, whereas this dye is so big it can be caught in the material. So if we put it in a membrane and make that membrane out of the woven material or the 1D material and have the colored sample on the left, then we can see how easy it is for these ions to transfer through the membrane. And yeah, so this is the membrane is made of PTFE. It's got small holes in it. Those can be covered up by either the 1D polymer or our 2D polymer. And then we just compare the ability of both of these to act as filters for those anions. When we've got the small anion, the small colored dye, that will pass through both types of material because it's smaller than the holes in the net, so it just passes through. But if we take the larger colored metal complex, this is 2.5 nanometers, so it's bigger than the holes in the net. It can still pass through the holes that we see in the 1D polymer, but it's trapped in the holes in the 2D woven polymer. And we see a much slower rate of passing of the dye through those systems. Okay, I've used up way too much of my time. I hope I've convinced you that knots and even woven, molecularly woven materials are now realistic targets for chemical synthesis. Knotted structures are abundant in nature at the molecular level. There must be reasons that biology does that. And now that we can make well-defined knots, we can begin to discover the consequences of having orderly molecular entanglements in materials. The introduction of knotting and weaving, of course, revolutionized the lives of prehistoric humans, being able to make nets and to tie, allowed humans to catch fish and feed themselves, being able to tie axe heads onto staffs, enabled them to make weapons to kill and hunt animals. Being able to weave allowed them to clothe themselves and to go and live in different climates. So the knotting and weaving revolutionized the history of humankind. Can nanoscale knotting and weaving also have an impact? We will all have to wait and see, and that's probably what your center is going to lead the way on. So thanks very much for having me. I haven't done any of this work, and I'd just like to thank my group for all their imagination and creativity and hard work. And thank you for having me. Thank you.